In this video, we'll look at simple linear regression. This is a concept covered in the CFA Level 2 syllabus under the quantitative methods topic. So for this video, I'm going to use a set of sample data. And here we have two variables. Okay, we have EV over IC, EV being the enterprise value and IC is the invested capital. So enterprise value is the market value of debt and equity. Invested capital is the book value of debt and equity. And over on this column, we have the spread between ROIC and WACC. So ROIC here is the return on invested capital, and WACC here is the weighted average cost of capital. So of course, in these two variables, we can come up, or we may want to investigate the statistical relationship between these two. Okay, we can probably say that if there is a positive spread, which means that the ROIC is greater than WACC, then that means the company should be creating wealth, which should lead to a higher EV to IC multiple. And if the spread is negative, which means the ROIC is less than WACC, that means the company is destroying wealth, and that should lead to a lower EV to IC multiple. Before we generate the regression output, it's always good to look at the scatter diagram to see if there is any relationship between these variables, whether it's linear or non-linear, or whether there is no relationship at all. So to generate the scatter diagram, you can click on the Insert tab and click on Charts here. Okay, select any of these. I'll take the first one, the scatter. All right, and then we need to select the data. Okay, add here, click on the add button, and our X values here will be for the independent variable, which is the spread. Okay, and then for Y values, before you select, remember to remove this. Okay, and then select the multiple. Okay, and then click OK. And click OK again, and then we have the scatter diagram. So I'm just going to edit the chart title. So this is EV to IC against the spread of ROIC and WACC. So on the vertical axis, I will just add the axis here, add chart elements, and for the vertical axis, this is EV to IC. Okay, and for the horizontal axis, this is ROIC minus WACC. Right? Now, of course, I'll just remove these grid lines here. Just click and delete, and click and delete, so it's cleaner. All right, and of course, we see on the preliminary stage, we see a positive linear relationship between these two variables. Okay, but if it's not clear enough, you can just right click on any of these points and click on add trend line. Okay, and over on this right hand side, we have a few options to select from. Okay, whether it's exponential, linear, logarithmic, polynomial, power, or moving average. But I'll stick with linear here, okay, for the straight line. So this is the line of best fit for this data. Now, of course, other things that you can do here is to, let me just go back to the earlier part, just click on the line here. So of course, we can also do things like display equation on the charts, okay, and also display R-squared value on the chart. Okay, so it's a quick way to actually generate the model and also tell us how accurate that model is, okay, statistically. So on the model here, it tells us that from the R-squared that 85.29% of the variation in the EV to IC multiple can be explained by the variation in the spread between ROIC and WACC. Then for the model here, the Y and the X, okay, so 3.137 here is the intercept, okay, on the vertical axis. So this tells us that when the spread is equals to 0, which means ROIC is equals to WACC, we should expect the company's EV to IC multiple to be 3.137. Okay, and for this 18.815 times here, okay, this tells us that for every 1 unit change in the independent variable, then Y will increase, or is expected to increase by 18.815. So since this is positive, so we should expect a positive change when X increases. Now, because X here is in percentage, so be careful when you interpret it. So when we say there is a 1 unit change, in other words, there is a 1% change or 1% increase in the spread, okay, 1% is 0.01. So if you take the slope, which is 18.815, okay, 18.815 times 0.01 or 1%, then there will be 0.18815. So based on this, because of the format of the axis, so this tells us that for every 0.01 change or 1% change in the spread, the EV to IC multiple will increase by 0.18815 times. So this is the expectation, okay, or estimation. So that's how we interpret the slope. But in normal cases, when we just interpret this, we will say that when x increases by 1 unit, then the dependent variable will increase by 18.815 units. Next, we are going to generate the regression output. So you can do this easily using the analysis tool pack. Just click on the data tab, okay, and then look for data analysis tool pack. Okay, so if it's not in, you will have to look for the add-in to add the analysis tool pack, right? So click on data analysis and then click on look for regression. Click OK. So you need to specify the input Y range and the input X range. So for the input Y range, that would be EV to IC multiple. You can select the label as well. And then for the X range, we'll select the ROIC minus WACC. So since I selected the labels, so just check on labels here. Okay, for confidence level, by default, it will include a 95% confidence interval. Then you may want to specify another confidence level. So maybe I'll just click on 99, just enter 99 here. Okay, and then for the output range, you can select it, the output to be in the same tab or whether it's in another tab. Okay, but I'm gonna just leave it in the same worksheet here. So I'm just gonna select the output range as, let's say, M1 here. Okay, and for the rest, I'm gonna just uncheck it. I'm not gonna do anything with it. Okay, and then just click OK. Right, so we have our regression output here. So let me just expand the columns so that we can see the output. So I'm going to just change this to 4 decimal places so it's easier for us to interpret. Okay, so this is to 4 decimal places, and same thing goes for this. All right, this as well. Okay, you can actually just change this to 4 decimal places too. All right, so now we have the regression output. We'll proceed to interpret the numbers and see how we obtain them. Right, so in the summary output, we have the regression statistics table, where we have the correlation coefficient. We have the R-squared, or we call it the coefficient of determination. Then you have the adjusted R-squared, which is useful if you have more than one independent variable. Then you have the standard error of the estimate, or we call this SEE, and this tells you that there are 30 observations. Okay, if you count here, we have 30 observations. Okay, there's 30 of them. And then we have the ANOVA table, which is to test the relationship between the dependent variable and the independent variables. But in this case, we only have one independent variable. And then this is the coefficients table. Now, just take note that there are 2 confidence intervals here. One is the 95% and the other is the 99% confidence interval. Alright, so first let's look at the correlation coefficient, which in this case is 0.9235. Okay, and this tells us that the correlation or the linear relationship between these two is almost perfect because the maximum is positive 1. Now, just take note that this multiple R is always positive regardless of whether the relationship is positive or negative. So always look at the slope, the sign in the slope, to confirm whether the relationship is positive or negative. So since this is positive, that means the correlation is positive. If this is negative, that means the correlation is negative, right? Now, then if you square the correlation coefficient, then you will get the R square. So like here, if I square the correlation coefficient, I'll get 0.852889, same number here. Okay, so there's a quick way for you to do that. There is another way for us to obtain this, as I'll show later on. Now, for these coefficients, we have interpreted this earlier. Okay, but just to show you how we can obtain this without using the regression output. Okay, so if you want to generate, let's say, the intercept, okay, and the slope, so we can use the intercept function. So just go for the intercept function here, select the y's and the x. So the y's here will be the EV to IC, comma, and then select the spread. Okay, and then of course we can lock this in. Okay, and then this will be 3.137. Okay, if you want to look for the slope, just copy this formula down and then change the intercept function to the slope function, and it uses the same input, so I just copied it here. So it's the same output that we have. Okay, same thing, right? So it's very simple. And then of course, once you get the intercept and the slope, the next part is you can do predictions based on that. Okay, so I'm not just going to move the scatter diagram down. Okay, so take note that the intercept value and the slope values are the same as what we saw in the diagram earlier. Okay, so it's just to confirm that it's correct. Okay, next what we can do is we can actually predict the multiple, okay, based on the model here. Okay, so this is our model. So I'm going to do a prediction here. So I'm going to do predicted. Okay, so I'm just use predicted EV to IC multiple. Just change this to bold here. Okay, now the model is very simple. Okay, it's based on EV. So the model here is based on EV equal to IC. This is our dependent variable equals to the intercept B0 plus the slope B1 times the independent variable, which is RIC minus WAP. Okay, so this is a model that I'm going to use here. So the predicted value will be equals to the intercept. So I'll just click on intercept. Okay, then just lock it in plus slope, lock it in. Then we multiply by the spread for each row. Okay, so this is what the model predicts the multiple should be, okay, for that spread. I'm going to copy this down here. So we have this predicted multiple. Now, after that, what we can do is, of course, other than using this to do the prediction, okay, later on we are going to predict based on new values as well. Now, you can also use other functions like trend. Okay, you can use a trend function. So for the trend function, it will take in the values, the data directly. So I can select the Y's, lock it in, the X, okay, lock it in as well. Okay, and then select the new X. The new X would be just this, the same thing, if I want to predict for the same set of data. And then comma. For constant, we'll usually set this to true, or you can put 1 for true. Okay, that means we'll assume that they'll calculate the value of B normally. Alright, so let's leave that as true or 1. Okay, and then you see we'll get the same set of values. Okay, it's the same. Okay, no difference. So it's up to you which method you want to actually use. Right? Now another way how you can do this is there's a function called forecast as well. Use forecast and look for forecast.linear. Okay, and then same thing, select, but for this you will need to select the value of X, which is a spread. And then the known Y's are what we have here, the multiples. And the known X will be the whole list of data. And then just click enter. Again, we have the same set of values. Alright, so whichever method you want to use is really up to you. But I'm just showing you different alternatives. So I'm going to erase this now. Okay, we don't need this actually because we only need this column. Alright, so we're done with that. So next part, what I'm going to calculate here is I'm going to show you how we calculate this standard error, which is the standard error of the model. This model itself. So for that we'll need the residuals. Okay, the residuals here would be the error term, okay, which comes at the end of the model, this E here. So the residual here is the difference between the observed data and the predicted data, the predicted number. So this, I'll take the actual minus the predicted. Okay, actual is also called the observed data, right? Then I will square the residual. Okay. So then we'll just we'll just copy the formula down and then we'll just total it up. Okay, so this gives us what we call the SSE. Okay, this is the sum of squared. This is the sum of squared errors, which is the same thing here. Okay, 18.9182, same thing. Alright, so if you want to get this standard error, it's very simple. Just take the sum of these squared residuals. Okay, and then we divide by the degrees of freedom. So for the residual, the degrees of freedom is based on the number of observations, which is in this case 30. Then we minus 1 because we estimated the intercept, and then we minus the number of independent variables, which is 1 here. So 30 minus 1 is 28. Okay, so that's why we have 28 here. So I'll just divide by 28. Okay. And then lastly, we need to square root. Okay, we need to square root these squared residuals. Okay, the mean of these squared residuals. So just click enter and we have 0.822. Okay, so it's the same result here. Just showing you how we get it. Now, of course, if you want to get the correlation here, okay, you can always use correl, the correl function, and select the arrays here. Okay, and then you can get the same answer. Okay, so of course in the exam, okay, they may or may not ask you to calculate the correlation coefficient from scratch. If they do, then you have to calculate the covariance and the standard deviation separately. For example here, if I want to calculate the correlation using the formula, I will need to calculate the covariance. Okay, I'll use covariance of the sample. So the covariance here between the two will be here, that will be 0.201, and then the standard deviation based on sample for the multiple, this is the y. Okay, and then the standard, now I'll calculate the standard deviation for the independent variable. Okay, and then to get this multiple, I will just take the covariance, divide by the standard deviation of x times the standard deviation of y. Okay, and we'll get the same number here. Okay, so there are many ways for you to actually calculate correlation, but I'll just leave that part out. Then after that, okay, now we have the standard error. So of course this measures the accuracy of the model. So if you're comparing multiple models, okay, with the same, for this, let's say with this different format of the variable, the one with the lower SEE, okay, we call this a SEE, the standard error of estimate. The lower the SEE, the more accurate the model is, okay, because it has lesser errors. The next part we'll look at is how we obtain this ANOVA table, this analysis of variance. So this is for the F-test. So earlier on I mentioned that for the residual, the degrees of freedom is the number of observation minus 1 for the intercept minus the number of independent variable, which in this case is just 1. So of course I obtained this 18.9182 here. And then now I'm going to obtain this RSS, which is the regression sum of squares, or what we call the explained variation. The next part I'm going to do now is I'm going to calculate this regression part here. And to get that, okay, to get the regression, we will need one thing. Okay, I will need to have the average of the multiples. So I'll need to have the average. So I'll just put average of the multiple. Okay, so that will be the average function. Okay, then I'll divide the whole thing here. Okay, and just lock it in so that the values are the same throughout. Okay, just copy it down. Now I'm going to calculate the regression sum of squares, or the explained variation. So to do that, okay, we'll take the predicted values minus the average, and then we'll square the difference. So I'll take the predicted minus the average, then we'll take the power of 2. So I'll just take predicted minus the average, okay, to the power of 2. Okay, and of course we'll just copy the formula down, and then we'll sum it up. Just copy over here. So we'll get around 109.6799 here. So the same number that we see here. All right. Now, of course, some people may not want to actually, do it for every row. They want to sum it up straight away. It's up to you. But if you want to do it in one line, okay, you can always use a very simple formula. Just take the bracket. Okay, just take bracket, and then just take the whole thing. Since I'll take the predicted, I'll highlight the whole predicted numbers here, minus the entire column here for the average. Okay, so for this average here, and then I'll close the bracket and square it. Okay, and of course we need to sum up the squared residuals, okay, the squared difference here. So I'll just put a sum, and then open bracket and close bracket. And whenever an array is involved for computation, remember to sum it up, don't just press enter. You need to press hold control and shift and press enter. So I'll hold control, shift and enter. Okay, and then we'll get the same numbers. Okay, so it's a quicker shortcut if you do not want to go through this hassle. But I'm showing you this to show you a systematic way of obtaining the numbers. All right. So once we get, of course, this is the regression sum of squares. Okay, this is the explained variation. This is the unexplained variation. If you total these two up, okay, you will get the total sum of squares, or the total variation. Okay, but to complete this, I'll just show you how we get the total variation. It will be the observed data, okay, minus the average. And then we square the difference. So the observed data here would be the first column minus the average. Okay, and then we square it. Okay, and then we'll get these numbers here. I'll just copy this down, and let's sum it up. Let's copy this over, and then it's 128,598. Okay, see that? Okay, so that's how you obtain the different variations here. Now, of course, before we move on, one thing to show you that how do we use these numbers to actually get the R-squared? Very simple. You can just take the RSS, the regression sum of squares, divide by the total sum of squares. Okay, then you will get this R-squared here. Okay. Or of course, in the textbook, they also mentioned that you can use 1 minus the SSE divide by the TSS. Okay, so that will be the same number as well. So take note that for this residual, the sum here is actually called SSE. Okay, it's the sum of squared errors. But for this, it's called SEE, the standard error of the estimate. Okay, so don't confuse between these two. Right, and then to get the mean squared errors, okay, the mean squared regression and mean squared of the residual, just take the sum of squares divided by the degrees of freedom. So in this case, if I take 18.9182 divided by 28, you will get 0.6757. And then, of course, this is 1, so the mean squared of the regression is also the same. Okay, for the total, the degrees of freedom is still n minus 1. Okay, but for the residual, be careful, is n minus 1 minus the number of independent variables. So to get the F statistic, we'll take the mean squared regression divided by the mean squared error. So in this case, if I take mean squared of regression divided by mean squared of the residual or the error, you will get this F statistic. Okay, of course, the larger this is, the more significant the hypothesis test will be. And this column here, significance F, this is the p-value for the F-test, which is very, very small, close to 0. And this focuses on the right tail for the F-test. So, of course, in Excel, how we obtain this, you can actually use f.f.dist.rt. Okay, it's giving, RT here stands for right. Okay, so the value of X here will be our F statistic. And for the degrees of freedom, we'll take the degrees of freedom in the regression, and then the next one will be the degrees of freedom in the residual. Okay, and then we'll obtain the same numbers. Okay, so this is more of a one-sided tail, the right tail. So in the F-test, take note that the hypothesis here for the ANOVA part for the regression is usually stating that, okay, that the slope coefficients, the beta 1 is equals to beta 2 equals to beta 3, and all the way up to beta k, and they're all equals to 0. Okay, so the null hypothesis states that actually there is no relationship between the independent variables and the dependent variable. And then for the alternative hypothesis, it states that at least, okay, at least one of the beta is not equals to 0. Okay, it's not equals to 0. So for this p-value that we see here, okay, if I'm assuming that I'm using a, let's say if I'm assuming I'm using a 5% significance level, okay, so this is definitely less than 5%, okay, less than 5% here. So if it's less than 5% means we'll reject the null. So we reject the null here. So our conclusion will be, okay, there is, okay, at least one of the variables or one of the slopes which is not equal to 0. Apparently here we are, of course here we only have 1. So in other words, when we are looking at simple linear regression, this whole thing is actually similar to your t-test. So here it's just saying that beta 1 is equal to 0, and for the alternative, beta 1 is not equal to 0 because there is only one independent variable here. So if I'm rejecting the null, that means my conclusion is that there is a statistically significant relationship between the dependent variable and the independent variable. Okay, so this is what the ANOVA test tells us. If this is greater than 0.05 or 5%, then we do not reject the null. That means there is no statistically significant relationship between the y and the x. Okay, now next part, we look at the t-statistic. Okay, the coefficients table here. So we have already interpreted the coefficients here. And then, of course, they have the standard error for this intercept and for the slope. And then we have the t-statistic. Now, this t-statistic is calculated using a default number of 0. Okay, that means you assume that the intercept is 0 and the slope is 0. Okay, so if you calculate it manually, I'll just show you. You can just take, for the intercept, we'll just take 3.137 minus 0, and then we divide by the standard error. Okay, so that's the same number. So again, I can repeat the same step, take the coefficient minus 0, and then minus 0, divide by the standard error. So I will get the same result here. Okay, and based on that, we can calculate the p-value. Okay, but of course, the regression output gives you that. So in this case, the p-value here is based on the two-tailed test. So be careful with that. So let's say, for example, if I'm trying to get the p-value for this slope coefficient, so I'll just take the t-test, okay, and then I'll use dot dist, and for a two-tail, so if I'm using a 5%, okay, if I'm using 5% here, so I'll just and then my degrees of freedom will be 28 for the residual, okay, and then just in this case enter. Okay, oh, forgot to select the degrees of freedom. So this so the x here, so for the value of x here will be the t-statistic, okay, and then for the degrees of freedom it will be 28. Just click enter, so you get the same numbers here. So this is for a two-tailed test. So be careful with hypothesis testing. So let's say in this case, if you are trying to, let me select this part here. So if the hypothesis test is asking you to test whether beta 1 is equal to 0 and beta 1 is not equal to 0, this is a two-tailed test. So for two-tailed test, you can compare this directly with 5% if you're using 5% as your significance level. So this is less than 0.05, which means we should reject the null. So our conclusion is there is a statistically significant relationship between ROIC and WACC, okay, the spread against EV to IC. Okay, so there is a statistically significant relationship between the two variables. All right, and take note that the p-value here, okay, is the same as the one we obtained under the F-test, okay, and then for the t-statistic, it has a special relationship with the F-statistic. So if I were to square this t-statistic, okay, I would actually get the same value as the F-statistic. But this only applies to a simple linear regression where there is only one independent variable. Let's say if you're trying to test for a right-tailed test. So in a right-tailed test, this is how it may look like. Beta 1 is less than equal to 0. And for here, the alternative test, beta 1 is greater than 0. This is a right-tailed test. So if you're doing this, then of course your p-value has to be halved. Okay, you need to divide by 2 because it's only one tail. Okay, so we have to take this value here, divide by 2. Okay, so again, of course, the result is very, very small, very close to 0. It's still less than 5%. Okay, so we will still reject the null. Okay, we will still reject the null, but this time the conclusion is, okay, there is a statistically positive relationship between the spread and the multiple. Okay, so this is to test for a statistical relationship, and this is to test for a statistical positive relationship. Okay, so be careful with what tests you are being asked to do on. Then the next part would be the confidence interval. Okay, of course we have 95% and 99%. I'm just going to show you how we do the 95%. Okay, and you can do it for 99%. So the general formula for the confidence interval is to take the coefficient. So I'm going to do it for the slope. Okay, so it's just the slope value, the coefficient, plus minus the critical t value times the standard error of the coefficient. So we already have the coefficients and the standard error here. We just need to know the t value, the critical value. So this critical value depends on the confidence level, okay, or the significance level in this case, and the degrees of freedom. All right, so let's do that. So the t value here, I'm going to use t dot inverse, okay, and this is dot 2t, which is for two-tail. The probability we're looking for, since this is 95%, so I'm going to use 0.05 or 5% in the tails. And then degrees of freedom will be 28. Okay, and the critical value here will be 2.04841. So let's try this. So I'm going to take the coefficient. Okay, I'm going to minus this critical value times the standard error. Okay, and then just click minus here. So you get 15.79. All right. So of course, if I copy the formula and then I just insert here and change this to a plus, let's see what I get. So do I get 21.8398? I do. Okay, so this is the critical t value. Okay, and then this is the lower and upper level. So we are 95% confident that the spread, okay, the slope of the coefficient here, okay, or the coefficient of this variable is between 15.79 to 21.8398. Okay, and of course for 99%, the t value will be larger. Therefore, the interval will also be wider. Right, so that's for the confidence interval. For the last part, we are going to do a prediction based on the regression model, and then we are going to also compute the prediction interval. So let's say that you have a company where the spread between ROIC and WACC is, let's say, 10%. So what should we predict the EV to IC multiple to be? Okay, and what variation would we expect? Okay, what's the prediction interval like? Okay, so for this case, let's say we will need to, I'll just use space here to specify. Okay, let's say the value of X here, okay, that we are trying to predict, the ROIC minus WACC here is 10%. Okay, and then we are trying to predict, okay, predict the EV to IC multiple. So in this case, based on the output, we have the intercept, okay, plus the slope multiplied by the spread, so that we should expect the EV to IC multiple to be 5.0185. Okay, but let's say I want to find the 95% prediction interval for this prediction. Okay, so to do that, we will first need to compute the variance of the prediction error. Okay, so the formula for the variance of the prediction error is based on the SEE squared. So let me just write that down here, so it's easier for us to refer to. So I'm just going to use a pen here. So the variance, okay, the variance of the prediction error, okay, is equals to the SEE square, okay, and then we multiply by 1 plus 1 over n plus the value of X here, which is 10%, minus the mean of X, then we square it, and then we divide by the n minus 1. This is the degrees of freedom for the total variation, and then we divide by the sample variance of X. Okay, so this will give us the variance of the prediction. And then once you get this, the prediction interval will be the predicted value of Y, the predicted value of Y plus minus the T value, okay, multiplied by the standard error of the prediction. Okay, so this is multiplied by S sub F. Okay, so the value of T is already obtained earlier. We got it as 2.04841 for a 95% interval. Okay, so this is for a 95% confidence level here. So the only thing we need to work out now is this, the variance of this prediction error. Right. So the variance of the prediction error. Okay, so we'll work that out. So just give some space. So before that, I will need to know what is the mean of X. Okay, the mean value. Okay, so let's work out the mean of the spread. Okay, and we also need to know the variance. Okay, the sample variance. Okay, variance of ROIC minus WACC. Okay, so I'll need some space here. So the sample variance would be based on standard that we can use a variance of dot S here. Okay, or we can even take the number that we computed earlier, okay, and square it, but I'll just do it fresh. So the variance of the sample for the spread, okay, let's highlight the spread here. So that will be 0.0106. Okay, and then the mean, okay, would be the average. Oops, sorry there. The average here would be the average. Well, the spread is about 8%. Okay, so let's calculate this variance here. So I'll just take the SEE squared, SEE here, squared, power 2. Then we multiply by 1 plus 1 over n. N here will be the number of observation, which is 30. Okay, and then we plus, lastly, this is the next part. So we plus bracket the value that we are predicting here for the spread is 10% minus the average 8%, and then raised to the power of 2. Then we divide by, open bracket, n minus 1 here is based on 30 minus 1, which is 29. And then we multiply by the variance, okay, which is what we compute here. And then we close bracket and close it again. So we get the variance. Okay, so now what we need to do is to get the prediction interval. So the 95% prediction interval here. There are two values here, of course. There's a lower and upper limit. There's a lower and the upper limit. Okay, so let's align this on the right hand side. So based on the prediction we have, this is 5.0185, lock it in, minus the t value. The t value here is 2.04841. Okay, based on the 95%. Then we lock this in as well. Okay, and then we multiply by the square root of this variance here. Okay, and then we get, remember to lock this in. Alright, so then I'll just copy the formula down and then just change this to a plus. And we have our lower and upper limit for the 95% prediction interval. So we can say that we are 95% confident that the predicted EV to IC multiple will be between 3.306 to 6.731. Okay, so that's for the prediction interval. Right, so that's the end of the video. You can actually find your own set of data and try to generate the output and interpret the results, okay, generate the scatter diagram. Okay, make sure you understand, of course, in a way what these numbers mean, and in terms of hypothesis testing, whether is it significant or not. Okay, so if it's less, so remember that the p-value, if it's less than your significance level, it means that the result is significant. We should reject the null. Okay, so and for these two cases, when you reject the null, that means there is a statistically significant relationship, okay, between the variables. But of course, be careful when you handle more than one independent variable. Then when you interpret the t-statistic, do be careful, because for the t-statistic, it only measures the relationship between that variable to the dependent variable. But for the F-test, it is to test the relationship of all the independent variables with the dependent variable. So you can say that ANOVA is a test of the whole model, but the t-test is to test for a single variable. Okay, so that's the end of this session.